So here's something to think about as you're lying there, settling in, letting the day fall away. Somewhere right now, in a lab, maybe in Vienna, maybe in Shanghai, maybe in a basement at MIT, there are two tiny particles, let's say 2 photons, 2 little packets of light, and they are connected to each other in a way that honestly still makes physicists a little uncomfortable. You could take one of those photons and keep it right there in the lab and send the other one across the room, across the city, across the ocean, or even, in principle, to the other side of the universe. And the moment you measure something about the one you kept, the other one, instantly, with no delay, no signal passing between them, seems to know what happened. It responds, it correlates, it matches. Not after a beat, not after some invisible message races across space at the speed of light. Instantly. That's quantum entanglement. And if it sounds strange, if it sounds like it shouldn't be possible, you're in very good company. Because it bothered Albert Einstein so much that he spent the last 30 years of his life arguing that it couldn't really work the way it appeared to. He called it spooky action at a distance, and he meant that as an insult. He thought it was proof that quantum mechanics, the theory that described it, had to be incomplete, that something was missing, some hidden layer of reality that would explain away the spookiness and make the universe sensible again. He was wrong. But getting to the point where we could prove he was wrong, that took decades, and some of the most beautiful, agonizing, clever physics ever done. And that story, that long, winding path from Einstein's discomfort to the astonishing experiments that settled the question, that's what we're going to walk through together tonight. Slowly. No rush. Just the story of how human beings figured out one of the strangest truths about the universe they live in. But let's not start with entanglement itself. Let's start earlier, because entanglement doesn't make any sense unless you first understand the world it grew out of, the world of early quantum mechanics, which was itself so bizarre that the people who invented it could barely believe what they were finding. So picture this. It's the very end of the 1800s, the 19th century. Physics, as a field, is feeling pretty good about itself. There's this famous sentiment, often attributed to Lord Kelvin, William Thomson, the great British physicist, that physics was essentially complete. The major laws were known. Newton's mechanics described motion. Maxwell's equations described light and electromagnetism. Thermodynamics described heat and energy. There were just a couple of small clouds on the horizon, a couple of little puzzles that hadn't been tidied up yet. That was the feeling. Almost done. Those small clouds turned out to be hurricanes. One of them was the problem of black-body radiation, how objects emit light when they're heated. Classical physics predicted that a hot object should radiate infinite energy at short wavelengths, which was obviously absurd. They called it the ultraviolet catastrophe, which is a wonderfully dramatic name for a math problem. And in 1900, a German physicist named Max Planck found a way to fix it, but only by making a very strange assumption. He proposed that energy wasn't continuous. It didn't flow smoothly like water from a tap. Instead, it came in tiny, discrete packets. Little chunks. He called them quanta, from the Latin word for how much. And here's the thing about Planck. He didn't really believe his own idea. He thought it was a mathematical trick, a convenient fiction that happened to give the right answer. He spent years trying to undo it, trying to find a way to get the same result without the quanta. He couldn't. Then, in 1905, a young patent clerk in Bern, Switzerland, you know who this is, Albert Einstein, took Planck's idea and ran with it. Einstein showed that light itself came in quanta, in little packets of energy that we now call photons. He used this to explain the photoelectric effect, which is the phenomenon where light hitting a metal surface can knock electrons loose. Classical physics couldn't explain why only light above a certain frequency could do this, regardless of how bright it was. But if light came in packets, and each packet carried an amount of energy proportional to its frequency, then it all made sense. Low-frequency light, no matter how intense, was just throwing lots of weak packets at the metal, none of them strong enough individually to knock an electron free. High-frequency light sent packets with enough energy each to do the job. It was beautifully simple, and it was, incidentally, the work that eventually won Einstein his Nobel Prize. Not relativity, the photoelectric effect. Now, think about what's happening here. In the span of 5 years, two of the greatest physicists alive have suggested that energy and light are granular, lumpy, discrete. This is deeply weird if you're used to thinking of the world as smooth and continuous, which everyone was, but it was just the beginning. Over the next 2 decades, things got much stranger. In 1913, Niels Bohr, a young Danish physicist, tall, soft-spoken, famously difficult to understand when he talked because he mumbled and trailed off mid-sentence, Bohr proposed a model of the atom where electrons could only orbit the nucleus at specific distances, specific energy levels. They couldn't just be anywhere. They were quantized, like Planck's energy packets. An electron could be in this orbit or that orbit, but never in between. And when it jumped from one orbit to another, it emitted or absorbed a photon with exactly the right energy to match the gap. This explained why atoms emitted light only at specific colors, specific wavelengths, those sharp spectral lines that had been cataloged for decades without anyone understanding why they existed. Bohr's model worked beautifully for hydrogen, the simplest atom. It didn't work as well for anything more complicated, but it planted a seed. It said, "The subatomic world has rules, and those rules are nothing like the rules we're used to." And then came the 1920s, and this is where things really accelerated. This is the decade when quantum mechanics, as a full mathematical theory, was actually born. And it happened in a rush, almost violently fast, driven by a small group of young physicists who were, in many cases, barely out of their 20s. Werner Heisenberg, a German, developed one version of the theory in 1925, matrix mechanics, built on abstract mathematical objects that didn't correspond to anything you could visualize. He was 23 years old. Erwin Schrödinger, an Austrian, developed a competing version in 1926, wave mechanics, built around a beautiful equation that described particles as waves. He was 38, practically elderly by the standards of this revolution. And then Paul Dirac, a quiet, almost pathologically reserved Englishman, showed that both versions were mathematically equivalent, different languages describing the same reality. But what was that reality? What did the math actually mean? This is where the trouble started. Because the equations of quantum mechanics were spectacularly good at predicting experimental results, you could use Schrödinger's equation to calculate the energy levels of an atom, the probabilities of different outcomes in an experiment, the behavior of particles in astonishing detail. The math worked. But when you asked what the math was telling you about what was actually happening, what an electron was actually doing between measurements, what the wave function actually represented, the answers were deeply unsettling. Here's the central strangeness, the thing you need to sit with for a moment. In classical physics, the physics of Newton and everyday experience, objects have definite properties at all times. A ball has a position. It has a speed. It has both simultaneously whether you're looking at it or not. That seems obvious, right? Of course the ball is somewhere. Of course it's moving at some speed. What else would it be doing? In quantum mechanics, that's not how it works. A particle like an electron doesn't have a definite position until you measure it. Before measurement, it exists in what's called a superposition, a kind of blurred-out combination of all the places it could possibly be, each weighted by a probability. It's not that we don't know where it is and we're just ignorant. It's that, according to the theory, the question, where is it, doesn't have an answer until the measurement happens. The act of measuring doesn't reveal a pre-existing fact. It creates the fact. Think about that for a second. Let it settle. Because this is the idea that made Einstein so profoundly uncomfortable, and it's the idea that eventually leads us straight to entanglement. Niels Bohr, along with Heisenberg and others, developed what became known as the Copenhagen interpretation of quantum mechanics, named after Bohr's institute in Copenhagen, where so much of this thinking happened. And the Copenhagen interpretation basically said, stop asking what the particle is doing when you're not looking. The theory gives you probabilities of measurement outcomes. That's what physics is. That's all physics can be. The wave function isn't a description of a real physical wave. It's a mathematical tool for calculating probabilities. Don't try to peek behind the curtain, because there's nothing behind the curtain. The measurement is the reality. Bohr was at peace with this. More than at peace. He thought it was profound. He thought quantum mechanics was revealing something deep about the relationship between the observer and the observed, about the limits of human knowledge, about the very nature of reality. He was philosophical about it, almost mystical at times. Einstein was not at peace with this, not at all. Einstein believed, deeply, stubbornly, brilliantly, that there had to be an objective reality independent of observation. The moon is there, whether you look at it or not, he reportedly said. He couldn't accept that physics had given up on describing what was actually happening in the world and had settled for merely predicting the outcomes of experiments. He thought quantum mechanics was correct as far as it went, but that it was incomplete. There had to be deeper variables, hidden variables, lurking beneath the quantum formalism, determining the outcomes that quantum mechanics could only describe probabilistically. And this disagreement, Bohr versus Einstein, Copenhagen versus realism, probability versus hidden variables, became one of the great intellectual battles of the 20th century. They debated at conferences. They exchanged letters. They argued through thought experiments of escalating ingenuity. At the 1927 Solvay conference in Brussels, Einstein started lobbing clever scenarios at Bohr, trying to show that quantum mechanics led to contradictions. Bohr, often after a sleepless night of furious thinking, would find the flaw in Einstein's argument every time. Einstein would come back with something more sophisticated. Bohr would parry again. It went on for years. And here's what's beautiful about this rivalry. It wasn't petty. It wasn't ego, not really. These were two men who genuinely respected each other, who were both trying to get to the truth. Einstein wasn't trying to destroy quantum mechanics. He was trying to show that it needed to be completed, extended, made whole. And Bohr wasn't dismissing Einstein's concerns. He was engaging with them fully, taking each challenge seriously, because he understood that Einstein's objections were the deepest and most dangerous ones anyone could raise. It was in this atmosphere of friendly, relentless intellectual combat, that entanglement first appeared, not in a lab, not in an experiment, in a thought experiment, a paper published in 1935 that Einstein wrote with two younger colleagues, Boris Podolsky and Nathan Rosen. The paper is usually called EPR after their initials, and it's one of the most important papers in the history of physics. Not because it was right exactly, but because the question it asked turned out to be even more profound than Einstein realized. The EPR paper proposed a scenario, a thought experiment, that was designed to show that quantum mechanics couldn't be the whole story. And the scenario involved two particles that had interacted and then flown apart, two particles that were, in the language we'd later use, entangled. Einstein, Podolsky, and Rosen argued that by measuring one particle, you could instantly know something about the other particle, no matter how far away it was. And since quantum mechanics said that the second particle didn't have a definite value until it was measured, this seemed to imply that your measurement of the first particle somehow instantly affected the second one across any distance, which was, Einstein argued, absurd. No influence could travel faster than light. Therefore, the second particle must have had a definite value all along, and quantum mechanics simply failed to account for it. It was a brilliant argument, clean, logical, devastating, or so it seemed. But the universe, as it turned out, had other plans. And understanding why Einstein's perfectly reasonable argument was wrong, understanding what nature actually does in this situation, requires us to go deeper into what entanglement really is, how it was eventually tested, and what those tests revealed about the fabric of reality itself. So let's do that. Let's slow down and really sit with what the EPR argument was saying, because it's one of those things that sounds airtight until you realize the universe doesn't play by the rules you assumed. Einstein's reasoning went something like this. Imagine two particles that interact and then fly apart in opposite directions. Quantum mechanics says these particles are described by a single shared wave function. They're entangled, though that word wouldn't be coined for another year or so. Now, according to quantum mechanics, neither particle has a definite position or a definite momentum until someone measures it. The properties are, in some deep sense, undetermined. Fuzzy, not just unknown to us, but genuinely not decided yet. That was the Copenhagen view, and it drove Einstein up the wall. Here's where his argument gets clever. Suppose the two particles fly apart, and you measure the position of particle A. Quantum mechanics lets you predict, with certainty, the position of particle B, because the particles are correlated. You don't have to touch particle B at all. You just know. Alternatively, you could have chosen to measure the momentum of particle A instead, and then you'd know the momentum of particle B with certainty, again, without touching it. Now, Einstein said, particle B is far away. Your choice of what to measure on particle A can't possibly affect particle B. That would require some kind of faster-than-light influence, which relativity forbids. So particle B must have had both a definite position and a definite momentum all along, whether you measured them or not. But quantum mechanics says a particle can't simultaneously have a definite position and a definite momentum. That's Heisenberg's uncertainty principle. Therefore, Einstein concluded, quantum mechanics is incomplete. There must be some deeper theory, some hidden variables, that describe what's really going on beneath the quantum fuzziness. It's a beautiful argument. Really it is. And if you're lying there thinking, yeah, that sounds pretty convincing, you're in good company, because a lot of very smart people agreed with Einstein. The logic seems watertight. But here's where things get strange and honestly, kind of wonderful. Bohr responded to the EPR paper almost immediately, publishing his own paper in the same journal later that same year, 1935. And Bohr's response was, well, it was Bohr being Bohr. Dense, philosophical, hard to parse. Even physicists who agreed with Bohr admitted his rebuttal was difficult to follow. His essential point was that Einstein was wrong to assume you could talk about the properties of particle B independently of the measurement setup for particle A. In Bohr's view, the two particles and the measurement apparatus formed an inseparable whole. You couldn't carve reality up the way Einstein wanted to. The entangled system was one thing, not two separate things with hidden instructions. Most physicists at the time sided with Bohr, but not necessarily because they found his argument crystal clear. It was more that quantum mechanics kept working. Every prediction it made turned out to be right. Every experiment confirmed it. So the pragmatic attitude was, Einstein raises interesting philosophical points, but the theory works, so let's get on with using it. The EPR argument was filed away as a philosophical curiosity. Interesting, maybe important someday, but not something that affected the daily practice of physics. And that's where things sat for nearly 30 years. Think about that. 3 decades. The most profound question about the nature of reality. Do particles have definite properties before you look, or does measurement create reality? Just sat there, unanswered, because nobody could figure out how to turn it into an actual experiment. It was philosophy, not physics, or so everyone assumed. Enter John Stuart Bell. And this is one of those stories where a quiet, unassuming person changes everything. Bell was born in Belfast, Northern Ireland, in 1928. His family wasn't wealthy. His father was a horse trader, and Bell was the first in his family to finish secondary school. He studied physics at Queen's University Belfast, then went on to work at CERN, the European Particle Physics Laboratory in Geneva. His day job was accelerator physics, designing the magnets and beams that smash particles together. Practical, hands-on engineering work. But in his spare time, on evenings and weekends and during a sabbatical year, Bell thought about the foundations of quantum mechanics. He thought about the EPR argument. He thought about hidden variables. And in 1964, Bell did something that Einstein, Bohr, and everyone else had failed to do. He found a way to turn the philosophical question into a testable one. He proved a mathematical theorem, now called Bell's theorem, that showed there was an actual, measurable difference between a universe where particles carry hidden instructions and a universe where entanglement works the way quantum mechanics says it does. Let me try to explain what Bell figured out, because it's genuinely one of the most elegant ideas in all of science, and you don't need a physics degree to follow it. You just need to think carefully about correlations. Imagine you and a friend are each going to receive one particle from an entangled pair. You're in separate rooms, far apart, and you can't communicate. Each of you has a detector that can be set to one of 3 settings. Let's call them setting 1, setting 2, and setting 3. When a particle arrives, you randomly choose a setting, and your detector gives you a result, either up or down. That's it. You write down your setting and your result, and you do this over and over, hundreds of times, thousands of times, with fresh entangled pairs each time. Now, after you're done, you and your friend get together and compare notes. You look at the cases where you both happen to choose the same setting, and you find perfect correlation. Every time you both chose setting 1, you got opposite results. Every time you both chose setting 2, opposite results. Same for setting 3. This is what quantum mechanics predicts for certain types of entangled particles, and it's also perfectly consistent with the hidden variable idea. Maybe each particle was carrying a little instruction set all along. If they measure setting 1, say up. If they measure setting 2, say down. And the two particles always carried complementary instructions. No mystery there, no spooky action needed. But here's what Bell realized. Look at what happens when you and your friend choose different settings. If the particles are carrying hidden instruction sets, there's a limit to how correlated your results can be when you measure different things. Bell worked out the exact mathematical limit. It's an inequality, a statement that says, if hidden variables are real, then a certain combination of correlations can never exceed a specific number. It's called Bell's inequality, and it's surprisingly simple. You can derive it with basic probability theory, no quantum mechanics needed at all. It's just logic and math applied to the hidden variable assumption. And then, and this is the kicker, Bell calculated what quantum mechanics predicts for those same correlations. And quantum mechanics predicts numbers that violate the inequality. Quantum mechanics says the correlations will be stronger than any hidden variable theory could possibly produce. Not by a tiny amount either, by a clear, measurable margin. So suddenly, after 30 years, there was a way to actually test this. You could build the experiment, measure the correlations, and check. Do they obey Bell's inequality, the way they would if Einstein was right and particles carry hidden instructions? Or do they violate Bell's inequality, the way quantum mechanics predicts? The universe had to pick one. There was no middle ground. But here's the thing. In 1964, when Bell published his theorem, nobody could actually do the experiment. The technology wasn't there yet. You needed to be able to create entangled particle pairs reliably, send them to separate detectors, choose your measurement settings randomly, and collect enough data to see the statistical pattern. That was extraordinarily difficult with 1960s technology. Bell himself was modest about his result. He published it in a relatively obscure journal, Physics Physique Physica, which was actually a short-lived journal that folded just a few years later. The paper didn't make a big splash at first. Most physicists were busy with other things. Particle physics was booming. Quarks had just been proposed. There was plenty to do without worrying about philosophical puzzles from the 1930s. But a few people paid attention. And slowly, through the late 1960s and into the 1970s, experimentalists started trying to build tests of Bell's inequality. The first serious attempt came from John Clauser, a young American physicist who had stumbled across Bell's paper as a graduate student at Columbia University. Clauser was fascinated. He was also a bit of a maverick. His thesis advisor and several senior physicists actively discouraged him from pursuing the topic. They told him it was a waste of time, that the answer was obviously going to agree with quantum mechanics, and that working on foundations of quantum mechanics was career suicide. In the physics culture of the late 1960s, questioning quantum mechanics wasn't just unfashionable. It was seen as slightly crackpot. Clauser did it anyway. He teamed up with Michael Horn, Abner Shimoni, and Richard Holt to reformulate Bell's inequality into a version that was more practical for real experiments. This is now called the CHSH inequality, after their initials, published in 1969. And then Clauser, working with Stuart Friedman at Berkeley, built the experiment. They used calcium atoms that emitted pairs of entangled photons, and they measured the polarization of each photon at different angles. The experiment was finicky. The equipment was temperamental. The count rates were low, which meant they needed long data collection runs to get enough statistics. But by 1972, Clauser and Friedman had their result. The correlations violated Bell's inequality. The data sided with quantum mechanics, not with hidden variables. Now, you might think that would have settled things, but science is careful. And this was an extraordinary claim. There were loopholes, subtle ways that the experiment might not be conclusive. The biggest one was called the locality loophole. In the Clauser-Friedman experiment, the detector settings were fixed in advance. They weren't changed randomly while the particles were in flight. So in principle, you could imagine some exotic hidden variable theory where the particles somehow knew what settings the detectors were going to use because the information had time to travel between the detectors at the speed of light or slower. It was a stretch, but it was a logical possibility. And in science, logical possibilities matter. Closing that loophole would require an experiment where the detector settings were chosen so quickly and so randomly that no signal, even traveling at the speed of light, could carry information from one detector to the other in time to affect the result. The particles would have to be far enough apart, and the settings would have to be switched fast enough that the two measurements were what physicists call space-like separated, meaning not even light could connect them. And that was a much harder experiment to build. The person who would eventually build it was a young French physicist named Alain Aspect, working in a basement laboratory at the University of Paris-Sud in Orsay. And the story of how he pulled it off, with equipment that was clever rather than expensive, and results that would help earn him a Nobel Prize 4 decades later, is one of those tales where you realize that sometimes the most important experiments in physics come not from the biggest budgets, but from the sharpest thinking. Aspect had first encountered Bell's theorem in the early 1970s, and it hit him the way certain ideas hit certain people, not as an abstract curiosity, but as an urgent, almost personal challenge. He was a graduate student at the time, and he did something that tells you a lot about his character. Before committing years of his life to this experiment, he traveled to Geneva to meet John Bell himself. He wanted to look Bell in the eye and ask whether this was worth doing. Bell, by most accounts, was both encouraging and cautious. He reportedly asked Aspect whether he had a permanent position yet, because pursuing this kind of foundational physics, the kind that many mainstream physicists dismissed as philosophy, could be a career risk. Aspect didn't have a permanent position. He went ahead anyway. And here's what made Aspect's approach so clever. The key problem, remember, was the locality loophole. You needed to change the detector settings while the photons were already in flight, fast enough that no signal traveling at the speed of light could carry information from one detector to the other. Clauser's experiment had used static polarizers. They were set before the experiment started and stayed put. Aspect needed something dynamic, something that could switch between measurement settings in nanoseconds. His solution was beautifully simple in concept, even if it was fiendishly difficult to execute. He used acoustic optical switches, devices that used ultrasonic standing waves in water to rapidly redirect photons to one of 2 different polarizers. The switching happened at a rate of about 50 megahertz, meaning the effective setting changed roughly every 20 nanoseconds. And here's why that mattered. The 2 detectors in his experiment were placed about 12 meters apart. Light travels 12 meters in about 40 nanoseconds. So if the switch flipped every 20 nanoseconds, the setting on one side could change while the photons were mid-flight, and there simply wasn't enough time for any signal, even one traveling at the speed of light, to carry news of that setting change to the other detector before its own measurement was complete. The 2 measurement events were space-like, separated. No communication was possible between them, not even in principle, not even by the fastest thing in the universe. Now, think about what that means for a moment. If you're a die-hard hidden variable theorist, your last refuge was the idea that maybe the particles were somehow coordinating with the detectors, that there was some kind of subtle signaling going on, some conspiracy between the source and the measurement devices. Aspect's experiment slammed that door shut. The detectors were making their choices too late and too fast for any such conspiracy to work. The experiment ran in 1982 at the Institut d'Optique in Orsay, just south of Paris. Aspect and his colleagues, Philippe Grangier and Gérard Roger in the key paper, used calcium atoms as their source of entangled photon pairs. They excited the calcium atoms with lasers, and as the atoms decayed, they emitted pairs of photons that were entangled in their polarization. These photon pairs flew off in opposite directions toward the two distant detectors, each equipped with the rapid acoustic optical switching system. The results were unambiguous. The correlations between the measurements on the two photons violated Bell's inequality by a wide margin, something like 5 standard deviations, which in physics is a very strong result. And because the locality loophole was now addressed, the conclusion was much harder to escape. Quantum mechanics was right. The correlations were real. They weren't caused by hidden variables carried along with the particles, and they weren't caused by any signal passing between the detectors. The entangled photons were exhibiting exactly the kind of non-local correlations that quantum theory predicted, and that Einstein had found so deeply troubling. But here's the thing about experimental physics. And this is something worth appreciating if you're still with me, lying there in the dark, maybe starting to drift. Every experiment, no matter how brilliant, has imperfections. And the physics community, to its credit, is relentless about identifying them. Even after Aspect's landmark result, people pointed out that there were still potential loopholes. Not the locality loophole. Aspect had dealt with that convincingly. But there were others. The most important remaining one was called the detection loophole, sometimes called the fair sampling loophole. And it's subtle enough that it's worth explaining slowly. In Aspect's experiment, and in Clauser's before him, not every photon that was emitted was actually detected. Photon detectors in the 1970s and 80s were far from perfect. They might catch, say, 5 or 10% of the photons that hit them. The rest just slipped through unnoticed. Now, the experimenters assumed, reasonably, that the photons they did detect were a fair, representative sample of all the photons being emitted. That's the fair sampling assumption. But what if that assumption was wrong? What if, somehow, the photons that were detected were a biased sample? What if the hidden variable theory was true, and it just so happened that the particles that would have given results consistent with hidden variables were the ones that went undetected, while the ones that got caught by the detectors were the ones whose behavior mimicked quantum correlations? It sounds conspiratorial, almost absurd, but as a strict logical possibility, it couldn't be ruled out. And in a question this fundamental, are the foundations of quantum mechanics correct? You can't afford to wave away logical possibilities. So closing the detection loophole required detectors that were efficient enough to catch essentially every particle. If you detect a high enough fraction of your entangled pairs, the math shows that no clever selection bias can fake a Bell inequality violation. And for photons, achieving that kind of detection efficiency was extraordinarily difficult with the technology available in the 80s and 90s. This is where the story branches out in an interesting way. Different groups around the world started pursuing different strategies. Some stuck with photons and worked on building better detectors. Others realized that you could use different kinds of particles entirely, particles that were easier to detect with high efficiency. One particularly important line of work used trapped ions instead of photons. Ions, electrically charged atoms, can be held in place by electromagnetic fields and measured with near-perfect efficiency. In 2001, a group at the National Institute of Standards and Technology in Boulder, Colorado, led by David Wineland and colleagues, performed a Bell test using entangled beryllium ions. Their detection efficiency was essentially 100%. Every ion was measured every time. And the result? Bell's inequality was violated. Quantum mechanics won again. The detection loophole was closed. But, and you can probably see where this is going, there was a catch. The ions were sitting right next to each other, just a few micrometers apart. So while the detection loophole was closed, the locality loophole was wide open. The two ions were so close together that signals could easily have traveled between them during the measurement. You'd closed one loophole, but left the other gaping. And this was the frustrating state of affairs for years. Decades, really. Photon experiments could close the locality loophole, but not the detection loophole. Ion experiments could close the detection loophole, but not the locality loophole. Nobody had managed to close both at the same time in a single experiment. And until someone did, a sufficiently stubborn skeptic could always find a crack to wedge doubt into. The quest to close all the loopholes simultaneously became something of a holy grail in quantum foundations. It was an engineering challenge as much as a physics one. You needed a source of entangled particles that were reliably produced, detectors that were incredibly efficient, and enough physical separation between the measurement stations that the locality condition was satisfied. Every one of those requirements pushed the limits of available technology. The breakthrough came in 2015, and it came from multiple groups almost simultaneously, which tells you that the technology had finally ripened to the point where this was achievable. The most celebrated of these was an experiment led by Ronald Hansen at Delft University of Technology in the Netherlands, and the way Hansen's team did it was ingenious. They used a technique called entanglement swapping, combined with nitrogen vacancy centers in diamond. Let me unpack that a little, because it's a beautiful piece of engineering. A nitrogen vacancy center is a defect in a diamond crystal where a nitrogen atom sits next to a vacant spot in the carbon lattice. This defect has an electron whose spin can be controlled and measured with remarkable precision. The Delft group had 2 of these diamond chips, placed in separate laboratories about 1.3 kilometers apart, far enough that light would need over 4 microseconds to travel between them. Each diamond chip could emit a photon that was entangled with the spin of its nitrogen vacancy electron. Those 2 photons were sent to a station midway between the labs, where they were subjected to a joint measurement, a Bell state measurement. When that measurement succeeded, it had the effect of entangling the 2 distant electrons with each other, even though those electrons had never interacted directly. That's the entanglement swapping part. You start with 2 separate electron-photon entangled pairs. You measure the photons together in the middle, and you end up with the 2 electrons entangled across 1.3 kilometers. Now, here's why this was so powerful. The electrons in their diamond chips could be measured with very high efficiency, over 95%, and the labs were far enough apart that the measurement choices and outcomes on one side were space-like, separated from those on the other. Both loopholes, locality and detection, were closed in a single experiment for the first time in history. The result? Bell's inequality was violated with a p-value of about 0.039. That's statistically significant, though not overwhelmingly so. The experiment was extraordinarily difficult to run, and they only accumulated a relatively small number of successful entanglement events over weeks of data collection. But it was enough, and other groups, one in Vienna led by Anton Zeilinger, another at NIST in Boulder, published their own loophole-free Bell tests around the same time, using different approaches, and they all agreed. Quantum mechanics was vindicated. The correlations were real, They were non-local in the precise sense that Bell had defined, and no local hidden variable theory could account for them. Zeilinger's group, it's worth mentioning, had been doing pioneering entanglement experiments for years, including a famous demonstration in 1997 where they achieved quantum teleportation of a photon's state, which we'll come back to later. Zeilinger, along with Aspect and Clauser, would share the 2022 Nobel Prize in Physics for their collective work on entanglement and Bell inequalities. 3 experimentalists, spanning 3 decades of increasingly refined tests, all circling the same profound question that Einstein had raised back in 1935. And what exactly had they proven? This is worth sitting with for a moment, because it's easy to state and hard to fully absorb. They had proven that if you create 2 entangled particles and send them far apart, the outcome of a measurement on one particle is correlated with the outcome of a measurement on the other particle in a way that cannot be explained by any theory in which the particles carry predetermined values and communicate no faster than light. That's what violating Bell's inequality means. Either the particles don't have definite properties until they're measured, which is the standard quantum view, or information is somehow traveling between them faster than light, or both, or something even stranger that we haven't thought of yet. Einstein would have hated this. He really would have. The man who gave us relativity, who showed that the speed of light is the ultimate cosmic speed limit, would have been deeply uncomfortable with the idea that entangled particles maintain correlations that can't be explained by any local mechanism. But the experiments are clear, and they've been replicated and refined so many times now that there's essentially no room for doubt about the empirical facts. What there is room for, though, is interpretation. And this is where the story takes a fascinating philosophical turn, because the experimental confirmation of entanglement doesn't tell you which interpretation of quantum mechanics is correct. It tells you that local hidden variables are out, but it doesn't tell you whether the wave function is real, whether many worlds exist, whether consciousness plays a role, or whether we need an entirely new framework to make sense of what's happening. And the debates around these questions are just as passionate and unresolved as they were in Einstein and Bohr's day, though they've evolved in ways that neither of those giants could have predicted. Because the landscape of interpretation today is richer and stranger and more contested than it's ever been, and the people arguing about it aren't armchair philosophers. They're working physicists who build experiments and publish papers and sometimes genuinely refuse to speak to each other at conferences. So let's talk about interpretations. And let's start with the one you've probably heard of, the one that dominated for decades, and that most physics textbooks still present as though it's the only game in town: the Copenhagen interpretation. We touched on this earlier when we talked about Bohr and Heisenberg in the 1920s, but it's worth spending a little more time with it now, because understanding Copenhagen is really the key to understanding why all the other interpretations exist. They're all, in one way or another, reactions to Copenhagen. The core idea of Copenhagen, at least in its most common form, goes something like this: a quantum system, an electron, a photon, whatever, doesn't have definite properties until it's measured. Before measurement, the system exists in a superposition, a combination of all possible states described by the wave function. When you measure it, the wave function collapses, and the system snaps into one definite state. That's it. That's the whole story. Don't ask what the system was doing before you measured it, because that question doesn't have a meaningful answer. The wave function isn't a description of reality. It's a tool for calculating probabilities. Shut up and calculate, as the famous phrase goes. though nobody's quite sure who said it first. Some people attribute it to Feynman, others to David Mermin, who actually used it somewhat ironically. Now here's the thing about Copenhagen. It works. It works phenomenally well. If you follow its rules, set up your quantum state, evolve it according to the Schrödinger equation, then use the Born rule to calculate the probability of each measurement outcome, you get predictions that match experiment to extraordinary precision. Quantum electrodynamics, which is built on this framework, has been tested to something like 12 decimal places. That's like predicting the distance from New York to Los Angeles and being accurate to the width of a human hair. So as a practical toolkit, Copenhagen is essentially unassailable. But as a description of what's actually happening in the physical world, it has some really uncomfortable features. The biggest one is the measurement problem. If everything in the universe is made of quantum stuff, atoms, electrons, photons, then measurement devices are also made of quantum stuff. So why does the wave function collapse when a measurement happens? What makes a measurement special? Where exactly is the boundary between the quantum world, where superposition reigns, and the classical world, where things have definite properties? Copenhagen doesn't really answer this. It just draws a line and says, on this side, quantum rules apply. On that side, classical rules apply. And don't worry too much about where the line is. For a lot of physicists, especially in the mid-20th century, this was fine. Physics is about predicting experimental outcomes, and Copenhagen does that brilliantly, so what's the problem? But for others, and Einstein was the most famous of these, though certainly not the only one, this felt like giving up. It felt like saying, we have a theory that works, but we have no idea what it means, and we're going to pretend that's okay. And this is where the story gets really interesting, because starting in the 1950s, people began proposing alternatives, not alternative theories exactly. The mathematical formalism of quantum mechanics was well established, and nobody was arguing with the equations. What they were proposing were alternative ways of understanding what those equations mean. Different ontologies, if you want the philosophical term. Different pictures of reality that all produce the same experimental predictions, but tell very different stories about what's going on underneath. The first major alternative came from a young physicist named Hugh Everett III, and it's one of the wildest ideas in all of science. Everett was a graduate student at Princeton in the mid-1950s, working under John Wheeler, who was himself one of the most creative and ambitious physicists of the 20th century. Wheeler had worked on the Manhattan Project, coined the term black hole, and had a knack for asking questions that made everyone else uncomfortable. He was the perfect advisor for someone like Everett. Everett's idea, which he published in his 1957 doctoral thesis, was breathtakingly simple in its logic, even if its implications are mind-bending. He said, look, the Schrödinger equation describes how quantum systems evolve over time. It's a beautiful, deterministic equation. The problem with Copenhagen is that it adds this extra postulate, wave function collapse, that isn't in the equation. Collapse is something we bolt on from the outside to explain why we see definite outcomes. So what if we just don't? What if we take the Schrödinger equation seriously and apply it universally to everything, including measurement devices and observers and the entire universe? If you do that, here's what happens. When a quantum system in superposition interacts with a measurement device, the device doesn't collapse the wave function. Instead, the device itself goes into superposition. and the observer reading the device goes into superposition too. The entire universe branches. In one branch, the electron went up and the detector registered up and you saw up. In another branch, the electron went down and the detector registered down and you saw down. Both branches are equally real. Both versions of you are equally real. You just can't see or interact with the other branch because the branches have decohered. They've become effectively separate from each other. This is the many worlds interpretation. And when you first hear it, it sounds absolutely insane. Every quantum measurement causes the universe to split. There are countless copies of you out there, living slightly different lives. It sounds like science fiction, and in fact, it's inspired enormous amounts of science fiction. But here's what's remarkable about it. Mathematically, it's actually simpler than Copenhagen. It has fewer postulates. It takes the wave function seriously as a description of reality and doesn't need to add any special rules about measurement or collapse. The price you pay is ontological extravagance. You get an unimaginably vast number of parallel universes, but the math is clean. Everett's thesis was not well received. Bohr reportedly dismissed it. Most physicists ignored it. Everett himself was so discouraged by the reception that he left academia entirely and went to work for the Pentagon, doing operations research and game theory for the Defense Department. He never published another paper in quantum physics. He died in 1982, at the age of 51, of a heart attack, having essentially given up on physics decades earlier. He never lived to see his idea become one of the most discussed interpretations in modern physics. And that turnaround is a story in itself. The many worlds interpretation was revived largely through the efforts of Bryce DeWitt, a physicist at the University of North Carolina, who championed it in the 1970s and gave it its catchy name. Everett himself had called it the relative state formulation, which, you have to admit, is much less exciting. DeWitt recognized the elegance of what Everett had done and started promoting it to a wider audience. By the 1980s and 1990s, many worlds had gained a serious following, particularly among cosmologists and quantum computing researchers, who found it a natural framework for thinking about quantum systems without having to worry about collapse. Today, surveys of physicists show that many worlds is the second most popular interpretation after Copenhagen, and among certain subfields, quantum information, quantum computing, cosmology, it might actually be the most popular. Sean Carroll, the Caltech physicist and author, is one of its most prominent advocates. David Deutsch, who we'll talk about more later because he's central to the story of quantum computing, is another. But many worlds isn't the only alternative to Copenhagen, and some physicists find it just as unsatisfying, just in a different way. If Copenhagen's problem is that it's too vague about what's real, many worlds' problem, critics say, is that it's too profligate. It postulates an infinite number of unobservable universes to avoid one awkward postulate about collapse. That's a steep price, and not everyone's willing to pay it. So let's talk about another approach, one that's been around even longer than many worlds, but that was suppressed, and I mean that almost literally, for decades. This is the pilot wave theory, also known as Bohmian mechanics, and its story involves one of the most unjust episodes in the history of physics. The idea goes back to Louis de Broglie, the French physicist who proposed in the 1920s that particles have wave-like properties. De Broglie actually suggested a version of pilot wave theory at the 1927 Solvay conference, the same legendary conference where Einstein and Bohr had their first great debates. De Broglie's idea was that particles are real. They have definite positions at all times, but they're guided in their motion by a wave, the wave function. The wave function is real too, and it acts like a pilot wave, steering the particle along its path. In this picture, there's no superposition of the particle itself, no collapse, no measurement problem. The particle is always somewhere definite. You just don't know where it is until you look, and the wave function tells you the probability of finding it in various places. It's a beautifully intuitive picture. But at the Solvay conference, Wolfgang Pauli raised objections, and Bohr's Copenhagen camp was so dominant that de Broglie essentially abandoned the idea. It lay dormant until 1952, when David Bohm, an American physicist with a remarkable and troubled life, independently rediscovered and extended it. Bohm's story deserves a moment. He had been a student of Robert Oppenheimer at Berkeley, and he was a gifted theoretical physicist. But in 1949, during the McCarthy era, he was called before the House Un-American Activities Committee because of his past associations with left-wing groups. He refused to testify against his colleagues, was arrested for contempt of Congress, and although he was acquitted, Princeton, where he was working at the time, refused to renew his contract. He was effectively blacklisted from American physics. He moved to Brazil, then to Israel, then to England, spending the rest of his career in a kind of exile. It was during this period of upheaval that Bohm developed his version of pilot wave theory. And here's the thing that's remarkable about it. Bohmian mechanics reproduces every single prediction of standard quantum mechanics. Everyone. It's empirically indistinguishable from Copenhagen, but it tells a completely different story about what's happening. Particles have definite positions. The wave function is a real field that guides them. There's no collapse, no measurement problem, no fuzziness about when quantum becomes classical. The cost is that the pilot wave is non-local. The wave function for an entangled pair of particles depends on the positions of both particles simultaneously, no matter how far apart they are. So when you measure one particle and it changes the wave function, the guidance of the other particle changes instantaneously. And this is where entanglement fits in so beautifully. In Bohmian mechanics, entanglement isn't mysterious at all. It's just a consequence of the fact that the pilot wave for a multi-particle system lives in a high-dimensional configuration space and guides all the particles simultaneously. The non-locality that Einstein found so troubling is right there, explicit, built into the theory from the ground up. It doesn't try to hide it or explain it away. It just says, yes, quantum mechanics is non-local, and here's exactly how. Now, you might be wondering, if Bohmian mechanics makes all the same predictions as standard quantum mechanics and solves the measurement problem, why isn't everyone using it? And the answer is partly historical, partly sociological, and partly technical. Historically, the Copenhagen interpretation was so dominant by the time Bohm published his work that most physicists simply weren't interested in alternatives. John von Neumann, the great mathematician, had even published what he claimed was a proof that hidden variable theories like Bohm's were impossible. And although that proof was later shown to be flawed, it discouraged a generation of physicists from even considering the idea. Bell himself, interestingly, was inspired to develop his famous inequality, partly because he was fascinated by Bohm's theory and wanted to understand what distinguished it from local, hidden variable theories. The sociological dimension is real too. For decades, working on interpretations of quantum mechanics was considered career suicide in physics. It was seen as philosophy, not physics. Real physicists did calculations. They didn't worry about what the wave function meant. This attitude is sometimes called shut up and calculate, and it was pervasive from roughly the 1940s through the 1990s. Young physicists who expressed interest in foundational questions were often warned by their advisors to stay away if they wanted tenure. That culture has shifted dramatically in recent decades, and one of the reasons it shifted is precisely because of the entanglement experiments we talked about. when Aspect and Zeilinger and Hansen showed that Bell's inequality is violated in the real world. It made foundational questions suddenly feel urgent and experimental rather than merely philosophical. If you can go into a lab and demonstrate that local hidden variables are impossible, then the question of what is actually going on becomes a scientific question, not just a philosophical one. And there are other interpretations too, each with its own flavor and its own community of advocates. There's the consistent histories approach, developed by Robert Griffiths and refined by Murray Gell-Mann and James Hartley, which tries to make sense of quantum mechanics without collapse by focusing on which sets of histories of a quantum system can be consistently assigned probabilities. There's the relational interpretation proposed by Carlo Rovelli, which says that quantum states aren't absolute. They're always defined relative to a particular observer, and different observers can give different but equally valid accounts of the same system. There's cubism, or quantum Bayesianism, championed by Christopher Fuchs and Rudiger Schack, which takes the radical position that the wave function doesn't describe the physical world at all. It describes an agent's beliefs about what they'll experience when they interact with the world. In cubism, quantum mechanics is a user's manual for navigating experience, not a map of reality. Each of these interpretations handles entanglement differently, and each has something interesting to say about what those correlations between distant particles actually mean. But here's what's crucial. And this is a point that sometimes gets lost in popular accounts. None of these interpretations currently makes a prediction that differs from standard quantum mechanics. They all agree on what you'll see in the lab. They disagree about what's happening when you're not looking. And that makes it genuinely hard to decide between them using the usual scientific method of testing predictions against experiments. Some physicists think this means the question is meaningless, that if two theories make identical predictions, there's no fact of the matter about which one is right, and arguing about it is like arguing about whether the number 7 is happy or sad. Others think it just means we haven't been clever enough yet to find an experiment that distinguishes them, and that eventually, one interpretation will make a unique prediction that can be tested. And still others think the question is meaningful, even if it can't be settled experimentally, because the interpretation you adopt shapes the questions you ask and the research programs you pursue, and that has real consequences for the progress of physics. This last point is actually really important, and it connects to something we haven't talked about yet, something that grew directly out of the entanglement research and the interpretive debates, and that has become one of the most exciting and practically consequential developments in all of modern physics. Because in the early 1980s, right around the time Aspect was doing his experiments in Orsay, a physicist named Richard Feynman stood up at a conference and made an observation that would change everything. It was 1981. The conference was at MIT, co-organized by MIT and IBM, and the topic was the physics of computation. Feynman was already a legend by then. Nobel Prize in 1965 for quantum electrodynamics, famous for the Feynman diagrams, famous for cracking safes at Los Alamos during the Manhattan Project, famous for being the most charismatic physics lecturer who ever lived. He was in his early 60s, still crackling with energy, still asking questions nobody else thought to ask, and the question he posed at that conference was deceptively simple. He basically said, "Look, if you want to simulate a quantum system on a classical computer, you run into a fundamental problem. The amount of information you need to keep track of grows exponentially with the number of particles. A system of just 40 or 50 quantum particles, not a lot, right, requires you to track more numbers than there are atoms in the observable universe. Classical computers simply cannot do it. They will never be able to do it. Not because our computers aren't fast enough, but because the mathematics itself scales in a way that no classical machine can keep up with." And then Feynman made the leap. He said, Well, what if instead of trying to simulate quantum physics on a classical computer, you built a computer that itself operates according to quantum mechanics? A computer whose bits aren't just zeros and ones, but quantum objects, superpositions of 0 and 1 simultaneously? A computer that uses entanglement as a resource, not as a curiosity? That, he suggested, might be able to simulate quantum systems efficiently, because it would be speaking the same language as nature. Now, Feynman wasn't the only person thinking along these lines. Around the same time, a physicist at Argonne National Laboratory named Paul Benioff had been working on the theoretical foundations of quantum mechanical models of computation, and he'd published some important papers in 1980 and 1982 showing that computation could in principle be carried out by a quantum mechanical system. And before both of them, back in 1973, Alexander Holevo in the Soviet Union had published foundational work on the information capacity of quantum systems. But Feynman's talk is the one that captured imaginations, partly because of who he was and how he said it, and partly because he framed the problem so vividly. He made people see that quantum mechanics wasn't just weird. It was computationally powerful in a way that classical physics wasn't. The weirdness was a feature, not a bug. And here's where David Deutsch comes in. And this is a name you should remember, because Deutsch took Feynman's intuition and turned it into something rigorous. Deutsch is a British-Israeli physicist based at Oxford, and he's one of those rare thinkers who works at the intersection of physics, computer science, and philosophy, and takes all three equally seriously. In 1985, Deutsch published a paper that described the first true universal quantum computer, a theoretical machine that could simulate any physical process, including quantum ones, efficiently. He showed that a quantum computer could do things that a classical Turing machine fundamentally could not. This was a huge deal. Alan Turing had established in 1936 that a single universal machine could compute anything that was computable, and that idea had been the bedrock of computer science for half a century. Deutsch was saying, actually, Turing's model is incomplete. There are computations that are physically possible, but that a Turing machine cannot perform efficiently. You need quantum mechanics to complete the picture. And Deutsch, by the way, is a committed many-worlds advocate. He's probably the most prominent physicist who explicitly argues that quantum computing only makes sense if you take the many-worlds interpretation seriously, that when a quantum computer performs a calculation, it's literally doing different parts of the computation in different branches of reality, and then combining the results. Not everyone agrees with that interpretation of what's happening inside a quantum computer, but it's fascinating that the interpretive framework we were just talking about directly shapes how one of the founders of quantum computing thinks about his own field. The interpretation you adopt really does influence the questions you ask. But for a while, quantum computing remained mostly a theoretical curiosity. People knew it was interesting in principle, but nobody had a killer application. A specific problem where a quantum computer would dramatically outperform a classical one. That changed in 1994, and the person who changed it was a mathematician at Bell Labs named Peter Shor. And this is one of those moments in the history of physics and computer science that genuinely sent shockwaves through multiple fields at once. Here's what Shor did. He developed an algorithm, now called Shor's algorithm, that could factor large numbers exponentially faster on a quantum computer than any known algorithm on a classical computer. Now, you might be thinking, okay, factoring numbers. That sounds like a math homework problem. Why would anyone care? And this is where it gets really consequential. The entire infrastructure of modern internet security, the encryption that protects your bank account, your emails, your medical records, the secure communications of governments and militaries, almost all of it relies on a mathematical assumption that factoring very large numbers is computationally hard. Specifically, most public key cryptography, including the RSA system that underpins most of internet security, works because if you multiply two large prime numbers together, it's easy to get the product. But going backwards, starting with the product and figuring out which two primes were multiplied, is extraordinarily difficult for a classical computer. We're talking numbers with hundreds of digits. The best classical algorithms would take longer than the age of the universe to factor them. Shor showed that a sufficiently powerful quantum computer could do it in a reasonable amount of time. Not instantly, but in polynomial time rather than exponential time, which in computational terms is the difference between possible and impossible. Think about what that means. If someone builds a large enough quantum computer, the encryption protecting virtually all digital communication on Earth becomes breakable. That's not a theoretical concern. Governments and intelligence agencies around the world took notice immediately. The National Security Agency, the Chinese government, the European Union. Everyone started paying very close attention to quantum computing after Shor's algorithm. And the reason Shor's algorithm works, the reason it can do what classical algorithms can't, is fundamentally connected to entanglement. A quantum computer doesn't just try each possible factor one at a time, the way a classical computer would. Instead, it creates a superposition of all possible inputs, processes them simultaneously through quantum interference, and uses entanglement to correlate the qubits in a way that makes the correct answer emerge with high probability when you finally measure the system. The entanglement between qubits is what allows the computation to explore an exponentially large space of possibilities without requiring exponential resources. It's not just parallelism. It's a fundamentally different kind of information processing that has no classical analog. The year after Shor's algorithm, in 1995, a physicist named Love Grover at Bell Labs, same institution, different researcher, developed another quantum algorithm, this one for searching unsorted databases. Grover's algorithm provides a quadratic speedup rather than an exponential one, which is less dramatic than Shor's result, but still significant, and it applies to a much broader class of problems. If you have a database with 1 million entries and you're looking for one specific item, a classical computer has to check on average 500,000 entries. Grover's algorithm can find it in about 1,000 steps. That's the square root of 1 million. For 1 billion entries, you'd need about 31,000 steps instead of 500 million. That matters. But here's the thing, and this is important to understand about where we are today. Building an actual quantum computer that can run Shor's algorithm on numbers large enough to break real encryption is extraordinarily difficult. As of the mid-2020s, we're still not there. The largest number that's been factored by a quantum computer using Shor's algorithm is tiny by cryptographic standards. The reason is a problem called decoherence, and it's worth spending a moment on this because it connects back to everything we've been talking about. Remember how we discussed that quantum systems exist in superpositions and entangled states? Well, those states are incredibly fragile. The moment a qubit interacts with its environment, absorbs a stray photon, gets jostled by a thermal vibration, feels the magnetic field of a nearby atom, it starts to lose its quantum properties. The superposition decays. The entanglement degrades. the quantum information leaks out into the environment. This process is called decoherence, and it's essentially the same phenomenon that explains why you don't see quantum weirdness in everyday life. Big, warm, messy objects are constantly interacting with their environment, so any quantum superpositions they might have decay almost instantly. The challenge of quantum computing is keeping qubits isolated enough from their environment that they maintain their quantum properties long enough to perform useful calculations, while simultaneously being able to manipulate and measure them with exquisite precision. This is an engineering challenge of almost unimaginable difficulty. Some approaches use superconducting circuits cooled to temperatures colder than outer space, about 15 millikelvin, which is 1/100th of a degree above absolute zero. Google, IBM, and others pursue this approach. Other approaches use trapped ions, individual atoms suspended in electromagnetic fields in ultra-high vacuum, manipulated with precisely tuned laser beams. This is the lineage of those ion trap experiments we talked about earlier, the ones Wineland pioneered. Still others are exploring topological qubits, photonic systems, nitrogen vacancy centers in diamond, neutral atoms held in optical tweezers. There's a whole zoo of approaches, each with its own strengths and weaknesses, and as of right now, none of them has definitively won the race. And there's another piece of this story that happened in between, something that connects the pure physics of entanglement to the practical engineering of quantum information in a way that still feels almost magical. In 1993, a team of 6 physicists, Charles Bennett, Gilles Brassard, Claude Crépeau, Richard Josa, Asher Paris, and William Wooters, published a theoretical paper proposing something called quantum teleportation. Now, before you get too excited, this isn't Star Trek teleportation. You're not dematerializing a person and rematerializing them somewhere else. What's being teleported is the quantum state of a particle, its complete quantum information, from one location to another, using entanglement as the channel. And the way it works is genuinely beautiful. You start with 2 particles that are entangled, say, 2 photons that were created together and share a quantum state. You send one to Alice and one to Bob, who can be arbitrarily far apart. Now, Alice has a 3rd particle whose quantum state she wants to teleport to Bob. She performs a special joint measurement on her entangled particle and the particle she wants to teleport. This measurement destroys the original state. You can't copy quantum information. That's a fundamental theorem called the no-cloning theorem. But it produces 2 classical bits of information that Alice sends to Bob through an ordinary channel, a phone call, an email, whatever. Bob then uses those 2 bits to perform a specific operation on his entangled particle, and when he does, his particle takes on exactly the quantum state that Alice's original particle had. The state has been teleported. The original is destroyed in the process, so it's not copying, it's moving. And in 1997, Anton Zeilinger and his team in Innsbruck, the same Zeilinger who would share the 2022 Nobel Prize, performed the first experimental demonstration of quantum teleportation using photons. They successfully teleported the polarization state of one photon to another across their laboratory. Since then, quantum teleportation has been demonstrated over increasingly large distances, across cities, through fiber optic cables, even between ground stations and satellites. In 2017, a Chinese team led by Jianwei Pan used the Michia satellite to teleport quantum states from a ground station in Tibet to the satellite in orbit, a distance of about 1,400 kilometers. That experiment was a landmark, and it pointed towards something that people in the field had been dreaming about for years: a quantum internet. a network where entangled particles distributed across the globe could enable fundamentally secure communication, distributed quantum computing, and applications we probably haven't even imagined yet. And the backbone of that network, the thing that makes it all possible, is entanglement itself. That invisible thread connecting particles across any distance, the very thing Einstein couldn't bring himself to accept, turns out to be the resource that could reshape how we communicate, how we compute, and how we understand the limits of what's possible with information. So let's talk about what a quantum internet would actually look like, because it's not just a faster version of the internet you're using right now. It's something fundamentally different. The internet you know works by sending classical bits, zeros and ones, through fiber optic cables and across wireless links. And it works beautifully for most things. But it has a deep vulnerability baked into its design, which is that anyone who can intercept those bits can, in principle, read them. We use encryption to protect information, of course, and modern encryption is very good. But here's the thing. Most of the encryption that secures your bank transactions, your emails, your medical records, it relies on mathematical problems that are hard for classical computers to solve. Specifically, things like factoring very large numbers, which is exactly what Shor's algorithm would make trivial for a sufficiently powerful quantum computer. So there's this looming tension. Quantum computing threatens the security infrastructure that the classical internet depends on. And the proposed solution, beautifully enough, also comes from quantum mechanics. It's called quantum key distribution, or QKD, and it uses entanglement, or closely related quantum properties, to create encryption keys that are provably secure, not because of mathematical difficulty, but because of the laws of physics themselves. The idea goes back to the 1980s. Charles Bennett and Gilles Bressard proposed the first QKD protocol in 1984, called BB84, which used individual photons prepared in different polarization states to establish a shared secret key between two parties. The security comes from a beautifully simple quantum principle. If anyone tries to intercept and measure those photons in transit, they inevitably disturb the quantum states, and that disturbance is detectable. Alice and Bob can compare a subset of their measurements over a public channel and check for errors. If the error rate is too high, they know someone was listening, and they throw the key away and start over. If the error rate is low, they know their key is secure, and they can use it to encrypt their messages with essentially unbreakable security. Now, BB84 doesn't strictly require entanglement. It works with individual quantum states. But in 1991, Arthur Eckert, who was then a young physicist at Oxford, proposed a different approach that does use entanglement directly. His protocol, called E91, distributes entangled photon pairs to Alice and Bob. Each of them measures their photon, and because of the correlations guaranteed by entanglement, those same correlations that violate Bell's inequality, they can generate a shared secret key. And here's what's clever. The security check is built right into the physics. If an eavesdropper has tampered with the entangled pairs, the correlations won't violate Bell's inequality in the expected way. So Alice and Bob can literally test Bell's inequality on a sample of their measurements, and if the violation is strong enough, they know their key is secure. The very thing that Einstein thought proved quantum mechanics was incomplete turns out to be the guarantee that nobody's spying on you. There's a kind of poetic justice in that. Both approaches have been demonstrated experimentally, many times, over increasingly practical distances. In 2004, a team in Vienna, Zeilinger's group again, they keep showing up, transferred a quantum-secured bank transaction across optical fiber. In China, a 2,000-kilometer quantum communication backbone called the Beijing-Shanghai Trunk Line became operational around 2017, connecting major cities with QKD-secured links. and the Meteus satellite that Pan's team used for teleportation. It also demonstrated satellite-based QKD, distributing quantum keys between ground stations separated by more than 1,000 kilometers. The satellite acts as a trusted relay, generating entangled photon pairs and sending one to each ground station. It's not a perfect solution yet. The satellite itself has to be trusted in some configurations, but it's a proof of concept for global-scale quantum-secured communication. But here's where the engineering gets really hard and really interesting. Distributing entanglement over long distances is not easy. Photons get absorbed or scattered as they travel through optical fiber. The signal degrades. In classical networks, you solve this with repeaters, devices that amplify the signal along the way. But you can't do that with quantum information because of the no-cloning theorem. You can't copy an unknown quantum state, so you can't just amplify it the way you'd boost a classical signal. This is one of those moments where a fundamental law of physics creates a genuine engineering constraint, and you have to find a completely different solution. The proposed solution is something called a quantum repeater, and it's one of the most challenging pieces of technology that the quantum internet requires. The basic idea, first outlined by Hans Briegel, Wolfgang Dürr, Juan Ignacio Chirac, and Peter Zoller in 1998, is to break a long communication channel into shorter segments. You create entanglement across each short segment, which is manageable because the distances are small enough that photon loss isn't catastrophic. And then you use a process called entanglement swapping to stitch those short-range entangled links together into long-range entanglement. Entanglement swapping is essentially quantum teleportation applied to entanglement itself. You take two pairs of entangled particles, say pair AB and pair CD, where B and C are at the same intermediate station, and you perform a joint measurement on B and C. This destroys the entanglement in the original pairs, but creates new entanglement between A and D, which might be much farther apart. You've extended the reach of entanglement without ever sending a quantum state across the full distance. It's an elegant idea. But building a working quantum repeater requires several things that are all individually difficult. You need quantum memories that can store entangled states long enough for the classical communication between nodes to happen. You need high-fidelity entanglement swapping operations, and you need error correction or purification protocols to maintain the quality of entanglement as you chain multiple segments together. As of the early 2020s, groups around the world are making progress on all of these fronts, but a fully functional, deployed quantum repeater network is still something that's being worked toward rather than something that exists. It's one of the grand engineering challenges of the field, and this is worth sitting with for a moment, because it illustrates something important about how entanglement has moved from philosophy to engineering. In the 1930s, Einstein, Podolsky, and Rosen raised entanglement as a thought experiment to argue about the foundations of physics. In the 1960s, Bell showed it could be tested. In the 1970s and 80s, Clauser and Aspect and others tested it. In the 1990s, people started figuring out what you could do with it: teleportation, quantum computing, quantum cryptography. And now, in the 2020s, the challenge is building the infrastructure to use it at scale. The questions have shifted from, is this real, to how do we engineer this? And that shift, that transition from fundamental physics to applied engineering, is one of the great stories of modern science. Let's zoom out a little and think about what else entanglement enables beyond communication and computation, because the applications are broader than you might expect. One area that's been generating a lot of excitement is quantum sensing. The idea is that entangled particles can be used to make measurements with precision that exceeds what's possible with classical techniques. This isn't science fiction, It's already being used. Gravitational wave detectors like LIGO, the Laser Interferometer, Gravitational Wave Observatory, which first detected gravitational waves in 2015, one of the great experimental achievements of the century, have begun incorporating squeezed light, which is a form of quantum-correlated photons, to push their sensitivity beyond the classical shot noise limit. The quantum correlations between photons allow the detector to reduce noise in the critical measurement channel, which means it can detect fainter gravitational waves from farther away. It's entanglement, or at least its close quantum cousin, quantum squeezing, making astrophysics more powerful. In medicine and biology, quantum sensors based on nitrogen vacancy centers in diamond, tiny atomic-scale defects that behave as exquisitely sensitive quantum systems, are being developed to image magnetic fields at the nanoscale. Imagine mapping the magnetic activity of individual neurons, or detecting the faint magnetic signatures of single molecules. These sensors exploit quantum coherence and, in some configurations, entanglement between multiple sensing nodes to achieve sensitivities that no classical sensor can match. And then there's quantum simulation, which circles all the way back to where we started with Feynman. Remember his argument at that MIT conference in 1981, that you need a quantum system to efficiently simulate another quantum system. That vision is becoming reality. Researchers are using small quantum processors, sometimes with just a few dozen qubits, to simulate the behavior of molecules and materials that are intractable for classical computers. This matters enormously for chemistry and materials science. If you want to design a better catalyst for industrial processes, or understand how a drug molecule interacts with a protein, or figure out why a certain material becomes superconducting at a particular temperature, you need to simulate quantum mechanics accurately. And for systems beyond a certain size, classical computers simply can't do it. The number of quantum states grows exponentially, and no amount of classical computing power can keep up. In 2019, Google's Sycamore processor performed a specific computation in about 200 seconds that the company claimed would take a classical supercomputer roughly 10,000 years. That claim, quantum supremacy, or quantum advantage, as some prefer to call it, was debated. IBM pushed back, arguing that with better classical algorithms, the gap wasn't quite so dramatic. But even the skeptics acknowledged that the experiment demonstrated something real. A quantum processor doing something that was at least extraordinarily difficult classically. And since then, groups in China and elsewhere have performed similar demonstrations with different architectures, including photonic systems. But here's the thing that keeps the field honest, and it's important to say this clearly. We are still in the early days. The quantum computers that exist today are what researchers call NISQ devices, noisy intermediate scale quantum. They have tens to a few hundred qubits, and those qubits are noisy, meaning they accumulate errors quickly. To run the really transformative algorithms, Shor's algorithm for breaking encryption, or large-scale quantum simulations of complex molecules, you'd need thousands or even millions of high-quality, error-corrected logical qubits. And each logical qubit might require hundreds or thousands of physical qubits to implement error correction. So the gap between where we are and where we need to be is still substantial. It's not a gap that people think is impossible to close. The progress has been remarkable, and major companies and governments are investing billions, but it's a gap that demands serious engineering breakthroughs in qubit quality, connectivity, error correction, and control systems. And woven through all of this, the quantum internet, quantum sensing, quantum computing, quantum simulation, is entanglement. It's the common thread, the resource that makes quantum technology quantum. Without entanglement, a quantum computer is just a collection of independent quantum bits, no more powerful than a classical machine. It's the correlations between qubits, the entanglement that links them into a coherent whole, that gives quantum computation its exponential advantage. Without entanglement, quantum key distribution loses its security guarantee. Without quantum correlations, quantum sensors can't beat classical limits. Entanglement isn't just a curiosity of physics. It's the engine of an entire technological revolution that's slowly, steadily taking shape. And that word, slowly, matters, because one of the most fascinating aspects of this whole story is the time scale. From Einstein's 1935 paper to the first quantum teleportation experiment in 1997, that's 62 years. From Bell's theorem in 1964 to the loophole-free tests in 2015, that's 51 years. From Feynman's 1981 talk to the first credible demonstrations of quantum advantage, nearly 4 decades. This is not a field that moves in quick, dramatic leaps. It moves in long, patient arcs, with decades of theoretical groundwork preceding each experimental breakthrough, and decades of experimental refinement preceding each practical application. And there's something deeply reassuring about that, something that speaks to the nature of how real understanding is built. Not in headlines, but in the quiet accumulation of insight, one careful experiment at a time. Which brings us to something that I think is one of the most profound and least appreciated aspects of the whole entanglement story. And it has to do with what entanglement tells us about the nature of reality itself. Because here's the thing. For most of the history of physics, we've operated under a pretty comfortable assumption. The assumption is that the universe is made up of stuff, and that stuff has definite properties, and those properties exist whether or not anyone is looking. Your coffee mug is sitting on the table right now, and it has a definite position, a definite color, a definite temperature, and those properties are just as real when you leave the room as when you're staring right at it. That's called realism, and it's such a basic, intuitive idea that it barely seems worth stating. Of course, the world is like that. Of course, things have properties independent of observation. What else could possibly be going on? And then there's another comfortable assumption, which is locality, the idea that things can only be directly influenced by their immediate surroundings. If you want to affect something far away, you have to send a signal, and that signal has to travel through the intervening space, and it can't go faster than the speed of light. That's not just common sense. It's baked into the structure of Einstein's relativity. Locality is what keeps the universe orderly. It's what prevents causes from outrunning their effects. It's what gives the word here its meaning, distinct from there. Now Bell's theorem, and this is why it's so staggering, why it deserves to be ranked among the most important results in the history of science. Bell's theorem tells us that we cannot have both. Not both realism and locality, not in a universe that produces the correlations we actually observe in entanglement experiments. The experiments have been done. The loophole-free tests have been run. The data is unambiguous. And the data says, pick one. Either the universe doesn't have definite properties until they're measured, or influences can somehow act across arbitrary distances instantaneously, or, and this is the option that makes most physicists uncomfortable, both assumptions fail simultaneously. Let that sit for a moment. This isn't philosophy. This isn't speculation. This is what the experiments demand, and different interpretations of quantum mechanics handle this dilemma in different ways, which is part of why those interpretations matter so much, even though they all make the same predictions for any given experiment. Copenhagen, the standard textbook interpretation, essentially gives up realism. It says particles don't have definite properties until measured. The wave function isn't a description of what's really out there. It's a tool for calculating probabilities. And when you measure one particle of an entangled pair, the wave function updates instantaneously. But that's not a signal traveling through space. It's just your knowledge changing. There's nothing weird happening in physical space, because the wave function wasn't in physical space to begin with. It's a clever resolution, but it leaves you with this nagging question. If the wave function isn't real, what is? What's actually happening between measurements? The many worlds interpretation takes the opposite approach. It keeps realism. The wave function is real, completely real, and it never collapses. Instead, every measurement causes the universe to branch, and all outcomes happen, just in different branches. Entanglement correlations arise because the branches are structured in a specific way. There's no non-locality, no spooky action, because everything that could happen does happen, locally, in its own branch. The cost? An incomprehensibly vast, ever-proliferating multiverse that you can never observe directly. Some physicists find that elegant. Others find it extravagant beyond reason. And then there's the pilot wave theory, Bohmian mechanics, which keeps realism. Particles have definite positions at all times, but explicitly gives up locality. In Bohm's picture, there's a guiding wave that connects entangled particles non-locally, and when you measure one, the guiding wave instantaneously steers the other. It's deterministic, it's clear, and it's honestly non-local. Some people find that refreshingly honest. Others worry about how to reconcile explicit non-locality with relativity. The point isn't that one interpretation is right and the others are wrong. The point is that entanglement has forced us into a situation where every available option requires giving up something we thought was fundamental about how reality works. And that's not a failure of physics. That's physics doing exactly what it's supposed to do, telling us that the universe is stranger than we assumed, and forcing us to update our assumptions. Now, there's a concept that's emerged in recent decades that I think beautifully captures what entanglement is really telling us, and it comes from the world of quantum information theory. The idea is this: maybe entanglement isn't just a weird feature of quantum mechanics. Maybe entanglement is telling us something deep about the structure of space itself. This idea has roots going back to a 2006 paper by Shinsei Ryu and Tadashi Takayanagi, who were working in the context of string theory and a framework called the ADS/CFT correspondence. Don't worry about the acronym. The idea is what matters. What Ryu and Takayanagi showed was a mathematical relationship between entanglement entropy, a measure of how entangled different parts of a quantum system are, and the geometry of space. Specifically, they found that the amount of entanglement between two regions of a quantum system corresponds to the area of a surface in a higher dimensional space. The more entanglement, the more space. Less entanglement, less space. Think about what that means. It's suggesting that the fabric of spacetime, the arena in which everything happens, the stage on which all of physics plays out, might not be fundamental. It might emerge from entanglement. Space might be stitched together by quantum correlations. And if you were to somehow disentangle parts of a quantum system, the corresponding region of space would pinch off, disconnect, tear apart. This idea was pushed further by Mark van Ramsdonk, a physicist at the University of British Columbia, in a 2010 essay that has become one of the most cited papers in theoretical physics. Van Ramsdonk argued, provocatively, but with solid mathematical backing, that entanglement is the glue that holds space together. Take a quantum state and gradually reduce the entanglement between its parts, and the dual geometric space develops a crack, a fissure, and eventually splits into disconnected pieces. Space, in this view, is not the container for entanglement. Entanglement is the creator of space. And here's what's really wild about this. Remember the EPR thought experiment? Einstein's whole objection was that entanglement seemed to imply some kind of connection between distant particles that violated the spirit of locality. He called it spooky action at a distance. But if space itself is built from entanglement, then there's a sense in which entangled particles aren't really distant at all. They're connected at a deeper level, a level beneath ordinary spatial geometry. The distance between them is, in some sense, an illusion, or at least an emergent, approximate description that breaks down when you look at the fundamental quantum structure. There's even a beautiful conjecture, proposed by Juan Maldacena and Leonard Susskind in 2013, called ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes, those tunnels through space-time that Einstein and Rosen described in a paper published, remarkably, in the very same year as the EPR paper, 1935. EPR refers to entanglement, and the conjecture says they're the same thing. Every pair of entangled particles is connected by a tiny, non-traversable wormhole. Every wormhole is a manifestation of entanglement. The two papers Einstein co-authored in 1935, which seemed to be about completely different topics, might actually be describing the same phenomenon from two different angles. Now, I want to be careful here. This is frontier physics. The ER equals EPR conjecture is exactly that. A conjecture. It hasn't been proven. The connection between entanglement and spacetime geometry is best understood in the specific mathematical context of ADS/CFT, which describes a kind of spacetime that isn't quite like our own universe. Extending these ideas to the real, expanding cosmos we actually live in is an open problem, one of the biggest open problems in theoretical physics. But the direction of the evidence, the mathematical hints, the way the pieces seem to fit, it's genuinely breathtaking. It suggests that entanglement isn't just a feature of quantum mechanics. It might be the most fundamental feature. The thing from which everything else, space, time, gravity, the geometry of the cosmos, ultimately emerges. And if that's true, then the story we've been tracing, from Einstein's discomfort to Bell's theorem, to aspects experiments, to quantum teleportation, to quantum computers, isn't just the story of a strange quantum phenomenon being gradually understood and harnessed. It's the story of physics slowly, painstakingly uncovering what might be the deepest layer of reality, the layer beneath space, the layer beneath time, the layer where the universe is, at its most fundamental, a vast web of quantum correlations. There's a phrase that the physicist John Wheeler loved to use. Wheeler was one of the great figures of 20th century physics. He worked on the Manhattan Project. He coined the term black hole. He was Feynman's doctoral advisor. And in his later years, Wheeler became increasingly convinced that information was the foundation of reality. He captured this in a slogan, "It from bit." Every physical thing, every it, derives its existence from information, from bits. The universe, Wheeler argued, is fundamentally informational. Quantum information theory has updated Wheeler's slogan. Now, it might be more accurate to say, "It from qubit." Everything from quantum bits, from quantum information, from entanglement. And that's not just a cute phrase, it's a research program. Hundreds of physicists around the world are working right now on understanding how spacetime emerges from quantum entanglement, how gravity arises from quantum information, how the smooth geometry of Einstein's general relativity is stitched together from the discrete correlations of quantum mechanics. It's one of the most active, most exciting frontiers in all of physics. And it all traces back to that 1935 paper, to Einstein, Podolsky, and Rosen, sitting down and asking what seemed like a simple question: can quantum mechanics really be complete? They thought the answer was obviously no. They thought entanglement was proof that something was missing, that quantum mechanics was an incomplete sketch of a deeper, more sensible reality. And in a way, they were right, but not in the way they expected. Something was indeed missing. What was missing was the understanding that entanglement isn't a bug. It's the deepest feature. It's not a problem to be explained away. It's the explanation itself. So where does all of this leave us? We've come a long way, from Planck's reluctant quantum in 1900 to the possibility that space-time itself is woven from entanglement. And I think there's one more thread worth pulling on before we let this story come to rest, and it has to do with something surprisingly practical, something that connects all of this high-level theoretical physics back to the world you actually live in, the world of real materials and real devices and real engineering challenges. Because the same entanglement that might underpin the geometry of the cosmos is also, right now, being engineered into the most precise sensors ever built, the most secure communication systems ever designed, and computers that operate on principles so alien to classical logic that we're still figuring out what questions to ask them. And the gap between the cosmic and the practical, between entanglement as the fabric of reality and entanglement as a tool you can build things with, that gap is not as wide as you might think. In fact, it might not be a gap at all. It might be the same thing viewed from two different angles. The way a mountain looks completely different depending on whether you're standing at its base or seeing it from a plane, but it's still the same mountain. Let's start with the sensors, because that's where the connection between fundamental physics and everyday usefulness is maybe the most immediate, the most tangible. You already know that entangled particles are correlated in ways that classical particles can't be, and you know that measuring one instantly tells you something about the other. But here's a subtlety we haven't really lingered on. Entanglement doesn't just correlate outcomes, it reduces uncertainty. And in the world of measurement, uncertainty is everything. It's the enemy. Every sensor ever built, every thermometer, every clock, every magnetometer, every gravimeter, is fundamentally limited by noise, by the random fluctuations that creep into any measurement process. Some of that noise is technical, things like electrical interference or thermal vibrations, and you can engineer those away with better shielding, better cooling, better design. But some of the noise is fundamental. It comes from the quantum nature of reality itself. It's called the standard quantum limit, sometimes the shot noise limit, and for a long time physicists assumed it was an absolute floor. You simply could not measure anything more precisely than this limit allowed. Period. Except that's not quite true. And the reason it's not true is entanglement. Here's the idea. Imagine you're trying to measure a magnetic field using atoms as your sensor. Each atom is like a tiny compass needle, and the magnetic field tips those needles by a certain angle. You measure the angle, you infer the field strength. Simple enough. But each individual atom gives you a slightly noisy reading because of quantum uncertainty. The spin of the atom isn't perfectly determined until you measure it. So you use lots of atoms, say 1,000, and you average their readings, the noise goes down. Specifically, it goes down as 1 over the square root of the number of atoms. Use 1,000,000 atoms, the noise drops by a factor of 1,000. That's the standard quantum limit, and it's exactly what you'd expect from classical statistics. More measurements, less noise, but with diminishing returns. Now here's what's clever. If you entangle those 1,000,000 atoms with each other before you make the measurement, you can do better. The correlations between the entangled atoms let you extract more information from the same number of particles. Instead of the noise going down as 1 over the square root of n, it goes down as 1 over n. That's called the Heisenberg limit, and it's a quadratic improvement. For 1,000,000 atoms, that's the difference between a factor of 1,000 and a factor of 1,000,000. That's not a small improvement. That's transformative. And this isn't just theory. Groups around the world have demonstrated entanglement-enhanced sensing in the lab. Atomic clocks at NIST and other national labs have used entangled ions to push timing precision beyond the standard quantum limit. LIGO, the gravitational wave detector, the one that first detected gravitational waves in 2015, confirming another of Einstein's predictions. LIGO has been exploring the use of squeezed light, which is a form of entanglement between photons, to reduce quantum noise in its measurements. The upgraded detectors, advanced LIGO with squeezing, can see further into the universe because entanglement lets them measure smaller ripples in spacetime. Think about that for a second. Entanglement, the thing Einstein called spooky, is now being used to confirm Einstein's own predictions about gravitational waves with greater precision than classical physics alone would allow. There's a beautiful irony there, and I think Einstein, for all his discomfort with quantum mechanics, would have appreciated the elegance of it. And quantum sensing goes beyond clocks and gravitational wave detectors. There are groups working on entanglement-enhanced magnetometers for medical imaging, measuring the tiny magnetic fields produced by neurons firing in the brain or by the electrical activity of the heart, with enough precision to map those signals in real time without the massive superconducting magnets that current MRI machines require. Quantum gravimeters could detect underground structures, water tables, mineral deposits, or tunnels by measuring minute variations in gravitational acceleration. Navigation systems based on quantum inertial sensors could provide GPS-level accuracy without any satellite signal at all, which matters for submarines, for spacecraft, for any situation where you can't rely on a signal from above. The military applications are obvious, but so are the civilian ones. Imagine self-driving cars that know exactly where they are, even in tunnels or urban canyons where GPS signals bounce and scatter. All of this rests on entanglement. The same entanglement. The same correlations that Bell proved couldn't be explained by hidden variables. The same non-local connections that troubled Einstein. The same quantum glue that might hold spacetime together. It's all one phenomenon, showing up at different scales, in different contexts, doing different work. Now, let's come back to quantum communication for a moment, because there's been real progress there that's worth mentioning as we bring this story toward the present day. Quantum key distribution, QKD, has moved well beyond the lab. China's Messias satellite, launched in 2016, demonstrated satellite-based entanglement distribution over distances exceeding 1,000 kilometers. In 2017, a team led by Jianwei Pan used Messias to perform entanglement-based QKD between ground stations in China and Austria, separated by 7,600 kilometers. That's intercontinental quantum-secured communication using entangled photons beamed down from space. It's not science fiction. It happened. The keys were generated, the encryption was performed, and the security was guaranteed, not by mathematical complexity, but by the laws of physics themselves. Any eavesdropper would disturb the entanglement and reveal themselves. The challenge now is scaling this up. Building a global quantum internet requires quantum repeaters, devices that can extend the range of entanglement without breaking it. Classical repeaters just amplify a signal, but you can't amplify a quantum state without destroying it, because of the no-cloning theorem. So quantum repeaters work differently. They use entanglement swapping, which is a protocol where you create entanglement between adjacent nodes, and then, through a series of measurements and classical communications, extend that entanglement to nodes that have never directly interacted. It's like a relay race, but instead of passing a baton, you're passing a correlation. Several groups have demonstrated entanglement swapping over fiber optic networks, and there are prototype quantum network test beds operating in the Netherlands, in China, in the United States, and elsewhere. We're still years away from a full quantum internet, but the pieces are being assembled. And when it arrives, it won't just be about secure communication. It will enable distributed quantum computing, where separate quantum processors are linked by entanglement to work as one. It will enable quantum sensor networks, where entangled sensors at different locations can make correlated measurements with precision that no individual sensor could achieve alone. It will be infrastructure, like the classical internet is infrastructure, but built on fundamentally different physics. And then there are the quantum computers themselves. We talked about them earlier. Feynman's insight, Shor's algorithm, the basic idea of qubits and superposition and entanglement as computational resources. But let me give you a sense of where things actually stand right now, because the reality is both more impressive and more humble than the headlines suggest. As of the early 2020s, the largest quantum processors have a few hundred to around 1,000 qubits. IBM's roadmap aims for systems with tens of thousands of qubits by the mid-2020s. Google, after their Sycamore demonstration in 2019, has continued pushing toward what they call quantum error correction at scale. And error correction is really the key bottleneck. Current qubits are noisy. They lose their quantum coherence, their ability to maintain superposition and entanglement, after very short times, microseconds to milliseconds depending on the technology. Every gate operation, every manipulation of a qubit, introduces a small probability of error. And quantum algorithms, especially the powerful ones like Shor's algorithm for factoring, require thousands or millions of gate operations. If each one has even a tiny error rate, the errors accumulate and the computation becomes meaningless. The solution is quantum error correction, and it's one of the most beautiful pieces of theoretical computer science ever developed. The basic idea, worked out in the mid-1990s by Peter Shor, Andrew Steen, and others, is that you can encode a single logical qubit across many physical qubits in such a way that errors can be detected and corrected without ever measuring the actual quantum information. It's like a self-healing fabric. The entanglement between the physical qubits protects the logical qubit from noise, but the overhead is enormous. Current estimates suggest you might need 1,000 or more physical qubits for every single error-corrected logical qubit. So to run Shor's algorithm on a number large enough to break modern encryption, you might need millions of physical qubits. We're not there yet. Not close. But the trajectory is clear, and every year the qubits get better, the error rates drop, and the architectures become more sophisticated. In the meantime, researchers are exploring what can be done with the noisy, imperfect quantum computers we have right now. the NISQ devices, variational algorithms, quantum machine learning, quantum chemistry simulations for small molecules. The results so far are modest, but they're real. And there's a growing sense that quantum advantage for practical problems, not just artificial benchmarks, but problems people actually care about, might first arrive in chemistry and materials science, where simulating quantum systems is the natural strength of quantum hardware, designing better catalysts, better batteries, better drugs, better solar cells. These are problems where the quantum nature of matter is the whole point, and where classical computers struggle precisely because they can't efficiently represent entanglement between electrons. And that brings everything full circle, doesn't it? Entanglement is what makes quantum chemistry hard for classical computers. Entanglement is what makes quantum computers powerful. Entanglement is what secures quantum communication. Entanglement is what enhances quantum sensors. And entanglement might be what holds the fabric of spacetime together. It's one idea, one phenomenon, one set of correlations, showing up everywhere, at every scale, in every context. And we've only been studying it seriously for about 90 years. We've only really understood it, to the extent that we do understand it, for maybe 60. And we've only been engineering with it for about 30. So here's the thing I keep coming back to, and I think it's a good thought to settle into as this story winds down. When Max Planck stood in front of the German Physical Society in December of 1900 and presented his quantum hypothesis, he didn't want to. He called it an act of desperation. He was trying to fix a mathematical problem with blackbody radiation, and the only way to make the numbers work was to assume that energy came in discrete chunks. He didn't think it was real. He thought it was a trick, a mathematical convenience that would eventually be explained away by proper classical physics. And yet, that reluctant, desperate idea cracked open the door to everything we've talked about tonight. Bohr's atom, de Broglie's waves, Heisenberg's uncertainty, Schrödinger's equation, Dirac's relativistic quantum mechanics, the EPR paradox, Bell's theorem, Aspect's experiments, quantum teleportation, quantum computing, quantum cryptography, and now the possibility that entanglement is the very architecture of reality. None of it was planned. None of it was foreseen. The people who built quantum mechanics were often uncomfortable with what they were building. Einstein never accepted it. Schrödinger was disturbed by his own equation's implications. Bohr embraced the strangeness, but couldn't fully explain it. Bell proved something profound and then spent years worrying about what it meant. And now, a century later, we're still arguing about the interpretation, still debating what's really going on when two particles are entangled, still unsure whether the wave function is real or just a tool for making predictions. And I think that's okay. I think that's actually beautiful, because it means the story isn't over. It means there are still deep questions waiting to be answered, still surprises hiding in the mathematics, still moments ahead when someone will sit down with a pencil and a piece of paper and realize something that changes everything. Maybe it will be the connection between entanglement and gravity that finally gives us a theory of quantum gravity. Maybe it will be a new interpretation of quantum mechanics that makes the whole picture suddenly click into focus. Maybe it will be an engineering breakthrough, a room temperature quantum computer, a global quantum network, a sensor so precise it reveals something about the universe we never expected. Whatever it is, it will be built on the same foundation, on the strange, beautiful, irreducible fact that particles can be correlated in ways that no classical explanation can account for. That measurement here can be connected to measurement there, instantly, without any signal passing between them. That the universe, at its most fundamental level, is not a collection of separate things, but a web of relationships, a tapestry of correlations, a story told in entanglement. And you know, that's not a bad thought to fall asleep to. The idea that everything is connected, not in some vague mystical sense, but in a precise, mathematical, experimentally verified sense. The particles in your body were forged in stars, and the quantum fields that make up those particles are entangled with fields everywhere else. You are, quite literally, part of the fabric, not separate from it, not observing it from the outside, part of it. So let that settle. Let the numbers and the names and the dates drift away if they want to. Let Planck and Einstein and Bohr and Bell and all the rest take their bows and step back into the quiet. What remains is the simplest version of the story. The universe is stranger than we thought, more connected than we imagined, and more beautiful than we had any right to expect, and we're still only at the beginning of understanding it. That's enough for tonight. That's more than enough. Rest well.